category. And it's a pleasure to me to present here this talk, especially since it is closely related to my first steps in mathematics, which were made namely in the Department of Algebra, and were devoted to the theory of integral representations. My talk is on the Grothendieck group K0 of A of an additive category A. When A is a locally finite category of a Dedekind ring, for instance, if all group of morphisms are finitely generated, that means when this Dedekind ring is integers, and A satisfy one more not too restrictive condition, I show that the Grothendieck group consists of two parts. The first is a free group, and it is indeed of purely local nature, that is only depends on the localizations of the category A. And the second is a sort of group of ideal classes of a maximal order in a semi-simple algebra. This talk were impossible without two persons who influenced my mathematical activity very much. The first was Andrei Reuter, who was my first advisor during my student years, and who involved me into the fascinating world of the theory of representations. The second was my colleague and co-author Hans-Joachim Bauers, with whom I made my first steps in the stable homotopy theory, and due to whom I made my first, I got acquainted in particular with the works on Freud, which were my original incentive to do the investigation presented here. I must also remind that Andrei Reuter had a great influence on the development of the Kyiv algebraic school, and a lot of us are highly in debt to him, so I dedicate my talk to his memory. This is the first, after some generalities, I touch localization and then formulate the main results. And then as a sketch of the proof, I consider K0 in local case, then K0 for genera, I will explain what does it mean. And finally, K0 in the global case. And as an application, I will show the easy proof of Freud's theory. So let R be a Dedekind domain with the field of fractions Q. Recall that an R category is a category A such that all sets of morphisms are R modules, and the multiplications of morphisms are bilinear. And I call A locally finite. All of these modules are finitely generated. If R is equals Z, the ring of integer, it means that all groups A, B are finitely generated abelian groups. The main example is the category lambda mod of finitely generated models of a finite R algebra lambda. That means R algebra finitely generated is R module. And another important example with R equals Z is the stable homotopy category SW of pointed polyhedra, or the same finite CW complexes. Recall that its objects are polyhedra with fixed point, and the set of morphisms is the direct limit of homotopy classes of continuous maps between iterated suspensions of X. It is known that this category is fully additive and locally finite over Z. In what follows, A is locally finite over the Dedekind ring, and fully additive or idempotent full, that is an additive category such that all idempotents indeed split. That means arise from direct decompositions. Recall that the Grothendieck group, K0 of A, is the abelian group generated by the symbols A bracket, where A run through objects of A, and with defining correlations, A bracket equals B bracket plus C bracket if A is a direct sum of B plus C. Just in the theory of numbers and or integral representation, the crucial role here plays the local global correspondence. I recall some main things. We denote, but consider these categories. The first tensor products of A with Q, with localization, with completion of localization, with the ring of quotient fractions of these completions. What does it mean? Tensor product must be just applied to all modules of morphisms. And I denote by QA, AP, the image of an object A from A in all these categories. Thus, for instance, AP from AP, VP, just this tensor product. And we must add some new operation at C, which defines the fully additive closure of a category. That means the smallest fully additive category containing C. This operation is necessary since extensions of scalars, like here, can imply appearance of new idempotence. For instance, if A is the subring of Z square, consisting of 4 pairs AB, such that A is congruent to B modulo 2, and A is the category of projective modules of A, there are no non-trivial idempotence in A as an object of this category, but there are non-trivial idempotence if we consider the rational envelope. This idempotent certainly do not split in this tensor product. The categories QA A hat P and QA hat P are called Schmidt categories. That is, every object from this category splits into a finite direct sum of indecomposable objects, and this decomposition is unique up to isomorphism and permutations of summands. The category AP, simple localization, is not necessarily called Schmidt, but it satisfies the cancellation law. If A plus C equals B plus C, then A is isomorphic to B. It follows from the fact that the natural functor from AP to the Kroll-Schmidt category AP dash reflects isomorphisms. So if the image of F is an isomorphism, so is F. Obviously, for a Kroll-Schmidt category C, the Grothendieck group is just a free abelian group with the basis consisting of the isomorphism classes of indecomposable objects. The natural functors from A to all these things induce the homomorphism of, that must be K0 of QA, K0 of QA, yes, and K0 of this one. The kernel we denote by K0 tilde. We use one more Grothendieck group, namely that of genera. I recall that the genus of an object is the set of objects which have all, such that all localizations of A prime are isomorphic to localizations of P, for all P. I denote by GA the set of genera of objects from A and define the Grothendieck group of this set. This is the group with just as for Grothendieck group of A. We just consider these things, and the relations are like this. If A equals B plus C. It doesn't depend on the choice of A, B, C from the genus. We have natural homomorphism of K0 JA to K0 QA with the kernel K0 tilde JA, and K0A to K0 GA. The kernel I denote by the class of A and call the class group of A. So there is a diagram of K0 groups like this. This is completion, this is localization, and so on. In what follows, we impose a restriction onto the considered categories. Namely, we say that A satisfies the max condition if for every indecomposable object W from its rational envelope, include everything obtained by splitting idempotence, there is an object S such that QS is isomorphic to W, and if we take endomorphism of S modulo nil radical, it is a maximal R order. It means that it is an R order such that there are no orders which are bigger than delta S and contained in the same rational algebra. One can easily show that if A satisfies the max condition, then its localization and completion of localization also satisfy this condition. Under this condition, the maps Q in this diagram, these maps are surjective. And then we have this decomposition. Yeah. This group is free, so we have it is a direct summand. And here with this, here K0 tilde groups. Now for every indecomposable object from QA, we fix an object S of W with this property. Yes, such that it is W, and this is maximal R order. and set S of A, the set of all these objects. If V is an object from QA, and then it decomposes into indecomposables, and we set S of V the direct sum of this S of WI. Now I formulate the main results. So A is always locally defined, fully additive, and satisfy the max condition. Then K0 tilde of AP is the same as K0 tilde from AP hat, from the completion. Then K0 of genera is isomorphic to the direct sum of K0 for localization, and as we have seen, the same of their completions. And finally, the class group of A is the direct sum of class groups of all these delta of W. Thus, the K0 of A consists of three parts, namely this group of classes, then this direct sum, and then K0 of QA ratio of rational envelope. This group I free, and this group is rather interesting. Yeah, this is this thing is the group of ideal classes of this maximal order. It is defined, for instance, in the book of Reiner maximal orders. If delta is commutative, so that means that it is Dedekind ring, then it's just a group of ideal classes in the usual sense. To prove this theorem, we relate the general situation to that of the theory of integral representations when all calculation can be done. And it is based on the following results, which is actually a variant of the Ioneda's lemma. Denote but add A, the smallest full subcategory of A containing A, and closed on the direct sums and direct sums. So we take all direct sums of A and their direct sums. Then the functor, the representable functor defined by A, induces an equivalence of this category with the category of finitely generated projective modules over the endomorphism ring of A. It allows us to study A piecewise instead of studying A, study these categories. Yeah, at least when we deal with the facts that involve finitely many objects. Just take for A the direct sum of these objects. We also need the following useful fact. If we have an object A, it always splits in two parts, where the first part is torsion. That means that its endomorphism ring as a torsion R model, and hence a model of finite length. And AF is torsion reduced. It means that its torsion part of its endomorphism ring is contained in the nil radical. So if we take this quotient, it is an order in the semi-simple algebra. And then, if we take morphism from torsion part to torsion reduced part, all of them are contained in the nil radical of the category. And it follows that if A is isomorphic to B, if and only B, the torsion part and torsion reduced part are isomorphic. So let's consider the full subcategories of A consisting of torsion and torsion reduced object. Then the K0 of A is the direct sum of K0 of these two parts. And K0 of AT is just a free abelian group with the basis of consisting of isomorphous classes of indecomposable objects. The last claim just means that this category AT is a Schmidt category. It follows from the fact that the endomorphism rings in this category are Artinian, and hence endomorphism rings of indecomposable objects are local, and then use Schmidt-Azumaya theorem. This corollary allows us to consider, if it is convenient, only the torsion-reduced part. Moreover, let's take the quotient of A modulo nil radical. This category is semi-primed, that it contains no nil ideals. And if we had ID0 A0, the image of the object A0, and as nil A is a nil ideal, Then A is isomorphic to B if all the images in A0 are isomorphic, and A is indecomposable if and only if A0 is indecomposable. And in particular, the Grothendieck group I is equal. Note that if A is indecomposable, then thing is either semi-simple Artinian or torsion-free and semi-prime. That means that our order in a semi-simple finite-dimensional Q algebra. And as we are interested only in torsion-reduced part, then we can deal only with this case, with the case of semi-simple finite-dimensional orders in semi-simple finite-dimensional algebras. Together with the previous observations, this allows to reduce most consideration to the case when this is category of lattices, that means torsion-free models, or when are ordered in a semi-simple. Okay, so we start our proof, the Sketchup proof. And first I consider this group in the local case. That means I consider this part of our diagram. This, okay? Yeah. So at the moment R is a discrete valuation ring. Then we have only this right part of our diagram. A is completion, rational QA, and rational QA head. One can easily prove that this diagram is Cartesian in the sense of the theory of categories. Again, up to isomorphism of functors, but it is commutative up to isomorphism of functors, and every object from here can be uniquely up to isomorphism obtained from a pair object, A prime from here and A double prime from here, which have the same image, isomorphic images here. Therefore, this commutative diagram of groups is also Cartesian, now in usual sense. And these groups are free, so this group is also free. Free abelian, I mean. Moreover, we are able to construct a basis of this group. First, consider we know that the basis of this group is the set of isomorphism classes in decomposables. Then I cross out these S objects. Yeah, and these objects, the remaining objects I call atomic objects, which are not S objects. For any atomic objects, one can find the smallest sum S of S objects, such that S tilde, this direct sum, lifts to an object of A. So we can add some S object and then lift it here. Then A is also indecomposable, and we call such an indecomposable object from A atomic. Actually, not all indecomposable objects from A are of this kind. And the object C, this one, is called the core of A. And I denote by A of A the set of isomorphic classes for atomic objects, and obviously it is 1-to-1 correspondence with this set, with cores. Yeah. Yeah. Namely, the key result is the following. If we take any indecomposable object B, which is not the S object, yeah, which is not consists of this maximal form, there are atomic objects A1 to AN and S objects S1 to Sn, such that B plus these S objects is isomorphic to the sum of atomic objects. And these objects, S1, Sn, A1, A, are uniquely defined up to isomorphism and permutation. The proof of this theorem is more or less straightforward, and I will explain by a simple example. Suppose that we have an object from this rational envelope, which is indecomposable, but its completion splits into 3 indecomposables. It can easily show such example even on the commutative level. Yeah. Then consider the atomic objects over completion, Cij, where I is not J. Yeah, such that their rational objects is the direct sum of Vi plus Vj. Then if we take this direct sum, yeah, it's a rational envelope with twice V1, twice V2, twice V3. So twice this one. So it lifts to an object B, which is also obviously which is indecomposable. And neither of these thing can be lifted to A. On the other hand, take this one, S of W. Then its completion is S1, S2, S3, just as this the completion. Yeah. And then consider the direct sum B plus S. Yeah, it is sum of this one plus sum of this one. And I group this one with this one and so on. And this is C tilde 1, 2. This is C tilde 1, 3, C tilde 2, 3. So we have B plus S is A1, 2, A1, 2, where these objects are atomic and Cij are their cores. The general procedure is almost the following. We decompose the completion like this, where C is the direct sum of atomic object and B prime has no atomic direct summons. So B prime consists of S summons. Then these objects are uniquely determined, and then I can construct some new thing. Yeah, such that, and we add some direct sum such that we have this thing, that just as in the example. This consideration implies the resulting theorem, namely the basis of this 3 abelian group K0 of A. I recall that A is local. Consists of isomorphic classes of atomic objects and S objects. And I recall that this one is, this thing is in one-to-one correspondence with this one. And this thing is in one-to-one correspondence with indecomposable objects of the rational envelope. So it gives the claim 1 of our main theorem, this claim, that this kernel is the same as this kernel. Okay. By the way, we want to obtain the following column, that if neither indecomposable object from QA splits in QA hat, then K0 of A is K0 of A hat. Then we don't, this thing is just, we don't need anything, don't need to add anything. So A is also Schmidt category. For instance, this is the case when A is a stable homotopy category. Now we consider the global case. And the following theorem gives the basis of the local global relations. Let A be fully additive and so on, and if nil and be the nil ideal. A, B be torsion, if A and B are torsion reduced objects, if there are such morphism that their products, both this one and this one, are scalar for some non-zero A, and if P1, PR are all prime ideals contained in A, then there are torsion reduced objects, A1 up to AR, such that their localization at PI is API, or other localization that's at B, and the direct sum of them is A plus R minus 1 times B. Note that A exists only in this case. And the second one, if we have different prime ideas so far, and we have a torsion reduced object of API, of this localization, and B such that B, there is a torsion reduced object of A such with the same rational envelopes. Then there is a torsion reduced object A such that its localization are just AI for this P1, PR, and all other localization are as in for B. To prove this theorem, we just pass to the semi-prime and torsion-free category AF0. And then we use this lemma, Yoneda lemma. Yeah. and replace this category by the category of modules over the endomorphism ring of the chosen object. Then we are in a situation well known in the theory of integral representations, where we can make necessary calculation and obtain the result. I will not go into detail. So now we can calculate the group K0 of genera. Namely, we say that an object in A is p-atomic if AP is atomic for atomic object from AP, and all other RS objects are S objects. Obviously, p-atomic objects are indecomposable, or this localization is indecomposable. And I denote by AAP the set of isomorphic classes for p-atomic object, and AA is their union. Now let A be any object of S, and S is the one. Then QA is equal to QS, so we have this morphism with the necessary conditions. And the global correspondences above give the following corollary. They are p-atomic objects such that A plus R minus 1S is their isomorphism. Okay. From this fact, one immediately obtained the structure of the group K0. Namely, K0 of JA is a free abelian group with this basis. And as AP is a one-to-one correspondence with this one, it gives the claim 2 of our main theorem, this one. So the whole group K0 is the direct sum of this free group and the kernel, this class group. To describe this kernel, we need a group structure on the sets arising from genera. It depends on two theorems, well known as the theory of integral representation, the Jacobinsky cancellation, and Reuter addition theory. I recall a Jacobinsky cancellation. Suppose that A be an object such that in the decomposition of this rational envelope of A0, all matrices are of dimension greater than 1, in all cases when F is non-commutative. And we have two objects from GA with this thing, then we can cancel A. The proof immediately reduces to the Jacobinsky cancellation for integral representation if we take the endomorphism ring of A. Okay. So in the arithmetic case, when Q is a global field, this condition is also necessary only if Fi does not satisfy either condition. For instance, if R equals Z, it should be imposed only in the case where this product is not a direct product of skew fields. And the Reuter addition theorem is the following: if we have A and B are such that QA is the additive envelope of QB, and we take any A prime from the genus of A, then there is B prime from the genus of B, such that A prime plus B equal A plus B prime. It is not so trivial because in general, for any A and B, this thing is A plus something that is of something from the genus of A plus B prime. Again, the proof is reduced to the classical case of integral representation if we take the endomorphism ring of this direct sum. This theorem implies the following corollary. If we take any two objects from GA and we call them congruent if A prime plus A equals A double prime plus A, this is an equivalence relation of this set, and the set of equivalence classes, class of A, becomes an abelian group if we define the addition in this way. The sum of classes is the class of A such that A prime dash plus A double dash is A plus A 3 dash. Note that we already know that the classes of A, the same of classes of lambda, where lambda is endomorphism ring of A. Using this structure, we can formulate the following result, which coincides with the claim 3 of our theorem. This one. The class group of A is the direct sum for all S objects of class groups of S. And the class group of A, I recall that the class group of A is the class group of this maximal order in the skew field. Yeah. Okay. Sketchup proof is very simple. Obviously, this class group is generated by these differences when A prime is from genus of A. If we take the S of QA, then Reuter theorem allows us to replace this difference by this difference for some. Yeah. So everything is reduced to the case of S objects. And then for S objects, again, using the integral representation, we can say that the classes, these classes in K0 are equal if and only if S prime is congruent to S double prime in J of A. Yeah, I will not. This lemma implies that class of A embeds here, and classes of A their sum, and then one easily shows that its sum is direct. And as an application, consider the stable homotopy category as W. It is a locally finite category of the ink of integers. It is well known. Yeah. And p-atomic objects are just what they call p-primary indecomposable polyhedra. P-primary means that the localizations of this polyhedron is not isomorphic to the localization of a bucket of spheres for fixed p, and all other localizations are isomorphic to the localization of a bucket of sphere. It is known, and is very easy to prove, that the only indecomposable objects in the rational envelope of the stable homotopy categories are just rational envelopes of spheres. Yeah, so these S objects are just spheres. And moreover, it is also well known that endomorphism of spheres is Z. So the no classes are. And so the class group of the stable homotopy category is 0. And we obtained the well-known theorem of Reuter. K0 for this category is the free abelian group freely generated by genera of indecomposable p-primary polyhedra. I think that I must stop, and thank you for your patience. And if you want to find the details, you can find it in the archive. Thank you very much.